as well as I forgot to record that.
Okay, should I start now?
Well, yeah, just hang on for a few seconds. Oh, okay. Now, did you get it, Sahil?
Yeah, I see it now.
Okay, good.
Let me start.
You could continue. Yes, sorry.
Yeah, all right. So I think maybe I will like to come back here for just a minute and explain to you something about it. I think maybe I rushed it. So any question till now? Like you are getting this, it's very simple, of course, and I hope you're getting the basic thing that we are.
But there is one, just for the benefit of the rest of them, although they're not asking the question. So here, when you use the Z3 interface, I guess the basic concept is clear. But are these variables Python variables X, Y, and Z that you have defined?
No, they are Z3 variables, but of course they are also Python variables here. But
yeah, that's what the question that I had was. So there are so you're not mixing the two things. Now everything is Z3 here, is it? No.
No, this
is
a library, right?
Python variables and Z3 variables.
Yeah, so actually a Z3 library that you have in Python, it's like overwrites all the operations. So for example, when I say X equal to Z3 real X, I'm just naming it. I can name it anything what I want. It doesn't matter. But after that, when I say X plus Y plus 7, so this plus is not like a normal plus. Z3 will automatically like create a new Z3 variable, variable for this part. And it will be like addition inside Z3. So it will somehow store. So for example, if I say print Z here, see what will happen. It will not actually output like some value. It will output X plus Y plus 7 because it's doing symbolically. So it's not actually evaluating this thing.
Yeah.
So
but what is the argument, the string argument X and Y that you give to this function? Why do you need that?
Okay, this is just name because when you retrieve the model, you want some name for the variable so that you can again go back and retrieve.
So that is the name in which it returns. It's not exactly X, Y, and Z. It is not X, Y, and Z on the left-hand side here. So it uses
so
whatever
if I name it, for example, let's say
that's
8 and I name weight, I just named that.
Okay.
Yeah, so I'm showing you. If I do it, so you see the model gives you age and weight. So it's just that these are like Python pointers or variables. They are pointer in Python, of course, internally. And here you actually give the name which will be used when Z3 will convert it into SMT4DL format. So it will Python will actually use these names for the variables. And for other variable, it will use some default name, like we won't even get them. If you don't define, for example, for Z, I have not defined a name, therefore I'm not getting it in the model. So if I want to get a value, then I should define it in the and define a name for that variable. Only then I'll get it in a model. But of course, it's internally included, but it's just not outputting the name of the value of the variable. That's it. I hope it's clear.
So it's kind of an alias, right?
Yeah, so when it's converting to SMT4DL format, so Z3 library is doing what? Like it's basically just taking your whatever you're writing in Python, it's just converting it into a really huge, not huge here at least, but in general, a huge SMT4DL code that you will write in, for example, that you write in riceforfun.com or whatever it is, and you don't need to do that manually. So this is all this library is doing. It's just it's the API, of course. Like these are just names that will be used when it converts them to SMT4DL format. That's it.
So you can do any Boolean combinations. You can use Boolean operators to take and, or, and so on.
Yeah, so for example, for ending, there is z3.end, then there is z3.or, z3.not, and you just pass those things. So this is what the functions are. But it also provides us a very cool thing that you can just also say is greater than. So Python will automatically understand that, okay, this is not like, it will convert it into greater than thing.
Some things are overloaded, like pluses and equality.
Almost most of the operators, like arithmetic operator, plus, minus, divide, multiply, and greater than, smaller than, all of these logical operators, they are overloaded. So that for the sake of convenience. So now you see, and it's giving age 0 and weight 0. Of course, because plus 7 is there. So, I mean, yeah, so I hope, okay, let me just put X plus Y and let's see what output it gives. You see it's giving me 6 and weight is 0 because of course it needs to find a value of x and y which so that x plus y is greater than 5. So it's just to the 6 and 0. So that's all it's doing. So any question till now for this particular small example? Okay, I hope not.
So
yeah, sorry, go on.
Right. So the like there are two kinds of sort of statements that we're defining here. So one is this defining these variables and then adding the assert. So basically anything in SMT2 that would be an assert is added to the solver specifically, right? And
no, actually the definition preceding that are automatically by default added. So if I have said z equal to x plus y, that is also added. So you are not required to do that manually. That's it.
Right. So it's just a shorthand that like we can just like it does that automatically for us, right? But it's internally actually like equivalent to defining a solver at the head of our code and then adding everything.
Yeah, it's actually exactly that.
Right.
Okay. All right.
So pretty much, this consists of, it does a lot of, translation. It defines, it does all the declaration like you saw, which I had to do explicitly for each of these variables. And all these equalities expressions are translated and equalities are asserted as atomic. And then everything is, asserted. So even though you were explicitly adding z is greater than phi, what the API did was a lot of smart things. Okay, so it kind of knew that
also,
was dependent on x plus y and all those things. It is adding as assertions.
Yeah, it's adding by default. Yeah, that's what happened.
A lot of work it's doing for you. Yeah.
Yeah. So there's one more thing. Like, go on.
Yeah, I have a question. So you said it adds z as well. So if you add another line underneath line on line 4, if you add z equal to 2, it's going to
that will actually make it a Python variable, and I don't think there'll be any sense in it. So it's unset because you were just because z was pointing to a z3 variable.
No. Why do you say? Because it says unsat because it is really unsatisfiable. That if z is equal to x plus y, I mean z is equal to 2, then z cannot be greater than 5. That's why it is. That's why
okay, wait, Professor Sahil, can you complete what you're saying?
Yeah, no, I was just confused about, so you said it adds z automatically. And if you add both z equal to x plus y and z equal to 2, or maybe if you add z equal to x plus y and something that contradicts another line. So I'm just saying.
Okay, I think it's a confusion with like, you have a confusion with how Python actually assigns variables. So if you know that Python actually.
No, that's fine. So here the way I understood it was that it assigns Z3 expressions to a variable, right? So you can write down any variable at x plus y and 2 and assign it to z.
Okay, let me actually test if you want that. Let me say x equal z equal to x. Is that fine?
Yeah, so line 3 will be irrelevant now, right?
Let's see.
No.
Yeah, it is irrelevant.
Huh?
Z greater than 5.
I think we are getting confused here. Okay, here's what I claim. All these things are added. The reason even before z is equal to 2 when you added, z is equal to x plus y is fine. Z is equal to 2 and z greater than 5 contradicted with each other. That's all. So everything is being added.
Okay, so here's a test for that. Write down z equal to 6. Write down z equal to 6 and z equal to 7. And I think it'll be sat.
Wait a minute. That okay, you are saying z equal to 7. Let's see what happens. Yeah, it's sat.
Now then it's a bit confusing. Okay.
It's not confusing. So I should like, that's why I wanted to say.
Yeah, why?
Let me just say 2 lines and I think that will be resolved, like all the confusion. So that's why I said to Sahil that maybe he's had some confusion on like Python variable assignment. So I said that because when you say z equal to, let's say I say x plus y, so what it's doing is z is, it's creating a variable x plus y, which is like a z3 real plus z3 real. So in the z3 library, they have defined and overridden the addition, and it will give you a new z3 variable, and that is set as z. Okay. Now, when I say something else, it will not it will just point that Z. So I say Z equal to X. It will point Z to the X. It will be a different Z3 variable. It will not have this thing inside it. So these are just definitions. So what you want to achieve, if you really want a many constraint on Z, then you add them here. So Z equal to X plus Y and Z equal to say X minus Y. Okay. And yeah, just something like that. And now maybe you can ask the same question. It says, okay, Y is equal to 0, because if Y is 0, then both of them are equal. So what you want to achieve is actually achieved by adding these equality things. So these are not assignments. These are like assertions that Z is X plus Y and Z is also X minus Y. That is what you want to achieve, then you add them inside the solver. But for the simple definition, you can just do it directly here. You don't need to write that assertion here. So this line, you can remove that if you're writing this thing. So this is just a shorthand kind of, but you cannot use it multiple times, like in writing C equal to X minus Y. Z3 won't like give a damn about this thing if it sees this line, like Python, sorry. So because it will assign Z to a new variable, not this variable.
So it'll take the latest one, I guess.
Of course, Python is interpreted language, so it just keeps the latest one. But if you want multiple assertion on Z, then you add them inside the solver as inside the dot add.
Yeah, here's a suggestion that I do. I will not mix these kinds of. That's why I asked if those variables are Python variables or Z3 variables. It will be terribly confusing to mix. It's not good practice to keep doing, to mix those things. I would just define them as variables, and then I would, keep them somewhat separate. Otherwise, you would get.
Yeah, that is also like, if it clarifies you, then you can do that. Sahil, does that answer your question?
Yeah, so that is how I understood it. I think it was confusing the way you phrased it earlier, which is that you said it adds it automatically, which I think was probably what misled us. Yeah.
Yeah, so when I mean, that's why I told you that
it's not like it adds it automatically, right? It's just that it stores the expression, any expression defined in Z, and then then Z.
Yeah, and it adds that expression. Yeah, it's that latest expression.
So it's just you store some expressions in a Python variable, and then it unrolls that in your sol.add or wherever.
Yeah, that's exactly. Yeah. So I think this made clear that, okay, if you want multiple, then do this. Okay. Let's not like, okay, anything else? Okay, cool. So here what we are doing is, so you remember the feed forward function then that we have in the network class. So there you give an input and it actually calculates the output, right? And actually in Python, if you want to do that, you will give it a value. So it cannot do the symbolic execution, but that's the thing with Z3. Z3 can do symbolic execution. So instead of giving it a value, this whole thing is just applying the feed forward. And I will explain in a short while how. So you just create a solver here. So I'm calling the function getSolver. And here I'm just the weights, sizes of the input and output. That's like pretty dumb. Let's just go here. So input of Z3 is Z3 real X underscore, and I add a string, and it's just this comprehension. I'm creating as many variables by the name x0, x1, x2 as the size of input. And similarly, I'm creating the variables y0, y1, y2 equal like till the size of output. And then I say feed forward Z3. This is a function which I'll explain in a while. Weight biases, I pass it input Z3 and I pass it to solver. Though I'm not using solver, I just passed it. Okay, we can remove that. Not for now. But yeah, so you just pass the weights and bias and you say the input Z3. So you understand this function, what you'll do is it will simply take the input, do the same thing that we do in the feed forward. So weights is a list of matrices. It will multiply the input with the matrices and add the bias, apply the activation function, which is redo here. It will do it until all the weights matrices are exhausted, and it will output the NAT thing. So remember, the output would be a huge symbolic execution. It will be like a equation explicitly written that, okay, you multiplying this and that with the variable x0, x1, x2. It will not actually calculate anything. So it will just give you a bunch of Z3 variables which have some value. And here I'm just saying that in the solver, I'm just saying that this y0 is equal to the first result, y2 is equal to the second result. And I'm doing this just because I only want these variables in my model. I don't care what happens in the intermediate layers. So I'm just doing this thing. So you will get it when I do the example. So this is not very necessary. Just look at the feed forward. So because Python, like Python Z3 library is so cool, so you don't have to worry too much about it. You just apply the, here I have weights and I have biases. I just say multiply matrix W with out. So what is out? Out is exactly XZ3. So XZ3 is.
So I want to emphasize here. So just to clarify, this is not evaluating. This is just returning expressions, correct?
Yeah. Symbolic execution.
So I want to emphasize that so that people, will not get confused. I know you did mention that, but what you're doing is eventually you want to pass these expressions. What is your ultimate goal? Maybe if you could first state that what your ultimate goal is. So you want to, what is it that you want to use Z3 to solve here? You want to solve for the weights?
No, not for the weights, of course. Weights and biases are given from the network. We don't want to solve for them. So we want to remember that we are here to check some properties of neural networks, right? So how do you check a property? You will usually say that if my input is like this,
so the inputs,
in this
the inputs are the ones that are variables. So you want to verify that. Okay, got it.
Inputs are like Z3 variables.
The weights are given, but you are generating the functionality defined by the neural network as a Z3 expression, symbolic expression.
Yeah, exactly. True. Okay, so
is that clear, guys?
Is that clear? I mean, I hope it is. Yeah, I mean, I was trying to explain something. Okay, I think it's clear, then I need not actually do much of it. Okay, let me just tell you something about this. So you have these neurons and you have these inputs. Instead of giving them value, I'm just saying, let's say X1, X2, X3. You have some bunch of weights here and there. You have some layers, and here is your output. So I'm naming this Y0, Y0, and this is Y1. And you are just doing the symbolic calculation for the whole thing, and the output that you get. So this will be a huge expression in this X1, X2, X3, depending on the weights, biases, and the activation, of course. And this is what you get here, and this is what you get here. So this is all we are doing. So remember the feed forward function. We are just applying the feed forward, but okay, I missed my, okay, yeah. So instead of doing it on the actual values, you are doing it symbolically on Z3 real variables. Okay. So here you multiply the matrix W with your input, and then you add a bias to it, and then you apply ReLU over it, and you see that this is only interesting function, apply ReLU. So here you just say Z3.if I0 is greater than 0, then I0 otherwise 0 for I in out. So this is basically saying that for all the values in the input vector, whatever is greater than 0, you output that. If it is not greater than 0, then you output 0. So this thing is like if then else. So if this is true, then this, else this. Yeah, that's it. So this is like feed forward using Z3. So because you cannot use NumPy multiplication and all, so I redefined all these functions, multiply matrix and add matrix. They are just like normal Python function that you will write for them. And Z3 will automatically take care of for you like that all these results are not actually values, they are symbolic expression. They're just expressions for your output. And
so
you will get a huge...
So here everything that begins with Z3 dot is a Z3 API call.
Yeah, and everything, every list and vector that you are using here, all of them are Z3. They're except weights and biases, these are like real numbers in Python. Otherwise, everything else like this out1, apply ReLU, these all our functions are acting over your Z3 matrices, like matrices of Z3 variables. Okay. So this is just like converting it to like what you're doing is this. So I mean, I just explained this. So you have this thing. Now what you say is for checking some property. For example, your input has some property that if you set x2 equal to 1, then you were expecting that y0 should be 1. So you can now write something like that. Okay, if I set x2 equal to 1 and you say y0 is not 1, okay? You do something like that. You add these two things to the solver, and then you just check whether this is satisfiable. So if this is satisfiable, it means that there is some model where you have x0, your x2, I meant x2, your x2 is 1, but your y0 is not 1. It means that your network is not working. Let's say if you wanted this property to be satisfied, that for all x2 1, y2 should be, y0 should be 1. So this is not being satisfied. So this is why we are doing this. So we are just applying the feed forward, and then we will add a few constraints over these x0 and these y0, y1 and x1, x2, whatever they are. And you will just ask whether for the solver to find a model for you. Remember, it won't work for huge networks. It will only work for a small one. So that's why actually I try to do this for our this thing, digit recognizer. Unfortunately,
if I may interject here, what you have done is, another way, if I want to rephrase, Madhukar last time showed in the Z3, he did it everything kind of manually. He did it by creating a function to denote the thing. What you're doing is you're generating it given a structure of neural net. Okay.
True. So I mean, sorry, I didn't know that Madhukar did all that already. So let me just quickly go through this. I mean, I've taken a lot of time. So you see here, I tried to apply this on this network for this digit recognition. Unfortunately, it gives me unknown, which means that it was not able to find.
Can you show before, where did you add the property that you want to verify?
So I'm not actually showing you this because this is not working. So I'll show you another example on ShapeNet, which is smaller. So I'm just telling you that this won't work always. So when your network is really huge, it might give you this unknown thing, which means that it didn't actually know whether it's set or unset because it was really...
that means Z3 timed out. Okay, but that's okay.
Timed out.
But even before timing out, which it did in this case, what did you check here? You added something to check, no?
Yeah, I wanted to check whether if I give it a, I took this picture of 9 and I just initialized the initial variables. So remember, it's like x0, x1, x2 till like x784, so 783. So I just said that if I just initialize half of them to these values, like I give a let's say a circle in between, and I will ask it whether the output could be, say, 2 instead of something else. Can a circle like a O kind of shape, can it give you 2 as an output? So that is what I wanted to check, but unfortunately it didn't work. So to make it clear,
that's okay. So, but where did you actually write the code that generated here? Okay, this is where you did. Okay, that's all I wanted to know. Okay.
Yeah. So that's why I'm showing you the actual example, because so that people will understand what's going on. Otherwise, they will get like, okay, this is not working, and I don't want them to be hopeless. So that's why I'm showing you an actual example over this. And so just give me a few seconds to get it done. Okay, this one is like very bad. Let's do it again. Yeah, this is good. Okay, we have 190 out of 200. Okay, now I'll explain everything. Okay, so you take the weights and biases from the ShapeNet. I mean, I know you know what ShapeNet is. And then I convert them to Python list. Here I'm converting them to Python list, from NumPy to Python list. And then I'm calling this function get solver, weights pi, biases pi. So I'm passing them the weights and biases, and I'm getting 3 things as output: solver, input Z3, output Z3. So remember, input Z3 is like a list, a matrix of x0, x2, x1, x2, x3, whatever the size of input is, and output Z3 is the y0, y2, y3, and whatever the size of output was, and that is what you are getting here, and you are getting the solver. So solver will contain all the actual assertion which will link the input and output. So input is like just with no constraint, and the output would depend upon the input, and solver has all those constraints inside it. So that's what we did in the initial, the first function that I was describing, the feed forward Z3. So I'll post this notebook on Moodle, and maybe you can take a look at it. So you just see it here. So what we're doing here is like I'm printing I'm showing you what input Z3. So here it is input, what input is. So it's like x0, x2, x1, x2, x3 till x15. So because there are 16 inputs, so there are 16 Z3 variable here. And you have this thing. Okay, just give me 1 minute. Yeah, so here I'm adding the actual, let's say the constraint. So what are the constraints? So I'm asking it to check something for me, which is, remember the square should be identified when the outer things are, let's say, very dark and the input thing is like really black. That is what we wanted. So Madhukar actually suggested me to check this thing. He said that what if we ask the solver to find us a picture, a matrix, where, I mean, let me go to the board for some explanation. Okay. So find me a matrix where the middle part, this is black, this is dark, and rest of it I don't care, and give me the rest of part so that the shape net actually gives me a square as output. So instead of identifying it as, it should have been identified as other if it was working properly, but it's identifying it as a square. That is what we are checking. So so remember, what is the index of this thing? 1, 2, 3, 4, 5, 6. So this would be 6, 7, 8, 9, 10, 11. So I just said these things, okay? Okay, sorry, okay. You set this thing, input, fifth input, that is the 6th actually. So start from 0 is greater than 0.8, 6th is greater than 0.8, the 9th is greater than 0.8, and 10th is greater than 0.8. So here I'm just telling it that in the input, all of these things, the middle portion, this should be, all of them should be greater than 0.8. So they should be dark. And then I'll ask it that in the output, I want so remember, output was this thing. So, I mean, if you remember, output is a like a 4x1 matrix, and you have like something here, let's say 0.9, 0.8, 0, 0. So whatever the largest value is, that will identify the shape. That is how we trained our network. And the first one, if the first one is largest, then it identifies as a square. If the second one is largest, then maybe it's L, and otherwise cap, and here it was others. So this is how we train the network. So what will I actually, so let me pose it as a question, because I think most of you won't actually like listen carefully. So if this is like, if I, let's name it symbolically y0, y1, y2, y3. So tell me the constraint that you will write that it should identify it as a square. So anyone?
So y1 is greater than, y0 is greater than all of the rest.
Yeah, y0 is greater than y1, y0 is greater than y2, and y0 is greater than y3. Cool, great. So that is all that you will add to your solver. You will just say that out C3, 0. And this 0 is just for the sake of convenience. You will understand when you look at the code. Just understand this y0. So this is y0 should greater than, okay, I think I wrote, yeah, here, sorry, y0 greater than y1, it's greater than y2 and greater than y3. So I'm doing all of them here, okay? And
so that's the constraint for it to return square, correct? Yeah.
Yeah, I'm saying that it should return, output should be a square, and input should have a bunch of like dark cells in the middle. That's what I'm input. That's what I'm saying. Okay. Then I also add a sanity bounds for this, that all the inputs should be between 0 and 1. That is something which we want. And here it's just adding this as a z3.end. Input z3 is greater than 0. Input z3i is smaller than 1 or equal to 1. And that's it. So let me run this and see. Okay, it's worked on the layers. It's giving me some, it's just printing this input z3. Let me also print out z3 just for the sake of like, you understand what's going on. So you see it's just y0, y1, y2, y3. But internally, remember, the solver somehow has all the constraints that are connecting these inputs to these outputs, and by using the weights and biases. So they're actually numbers. There's no symbolic number here in weights and biases. Okay, let's check for whether it's giving me, okay. All right, it's taking a while. I think okay, it's giving me a set. So here what we are doing, let me, instead of like doing, okay, let me just check the model and see what's giving me as a model. Okay, it's giving me some model. Of course, this is very hard to understand. So here is a function which is written to actually output what the model gave. Okay, so here I'm just, you can look at the functions and see how they are working. So here we are just somehow calculating, getting the value of x1, x2, all the inputs. And remember, we didn't set all the inputs. We only did set few of the inputs, namely x5, x6, and x9 and x10. So you just run this and see. So it's giving me this thing. And you see, it's kind of like magic. I mean, at least I was impressed by this. So it's giving me a matrix where all of these things are red, let's say very close to 1. And all of these things are, I mean, for some reason, very close to 0. But the output that the network is giving me is a square. So it's giving me a counterexample that, yeah, my model is not actually satisfying this particular property, that the middle portion, if the middle portion is red, then it should actually identify as other, not as a square, right? So this is what we are getting from here. Yeah, if this model was unset, like then we would know that, okay, our network is pretty cool. But you see here, it's getting 190 out of 200, correct? So if you actually randomly pass a matrix to it, I mean, maybe like you just see this, it's actually working pretty good. So if I pass it a square-like thing, it's giving me a square. But if I increase these things, let's say 0.9, 0.9, I don't think it will give me a square. Let's see, it's giving me other, because I made these things as dark. So you will expect on a like, just when you look into this network, you'll say, okay, it's pretty good. If my middle portion is like reddish, then it won't give me square. But here you are getting a counterexample, an actual list. So let me print the list for you. Okay, and see, this is giving me an example that, okay, if you pass this value, your network will give you a square, but it's definitely not a square because the middle portion shouldn't be happily dark. So this is what testing and all thing that we are going to do here. Is there any question till now or anything? Any comment?
I just wanted to, like, you had this function to generate a model for a given neural network, and it is also returning a solver to you, right?
Yeah,
so
Z3 solver, yeah.
Constraints, yeah, so what constraints are you adding inside that function for that solver?
Yeah, the solver
like
is basically, yeah, it's like feed forward. I told you, right? This function, it's like this get solver function, right? So it's just calculating that the input and output should be connected by the weights and biases. So I'm inputting the network. So a network is identified exactly by the weights, biases, and activation function. So I have assumed it's ReLU activation. So weights and biases are given. So you are just applying this, you are applying the feed forward on symbolically on this vector, okay? And you are getting the output. Yeah. These constraints are inside this solver.
Yeah, so if I may state in another way, paraphrase thing. So it is exactly creating an expression. I mean, it is expressing as a bunch of constraints. You remember that Madhukar showed with that very toy example, a set of formulas that are related, each node, the output at each node in terms of the, as a function of the inputs to that node. And that he did for each of the nodes, and then took a conjunction of those whole things all the way until you, there was the output layer. That's what he thought is generating, okay? It's a whole
like, yeah, if you still have a doubt, you can continue. Sorry.
Yeah, so you could do that in several ways. I mean, you could make them all into one big expression, okay? Or you could do it as a conjunction of constraints that relates the output at each node relative with the inputs coming into that node.
Right.
Those are all expressions. Huh?
Yeah. So I get that. So what we're doing here is kind of generating one huge expression in the feed forward Z3 function, right?
Correct.
And then with the constraint we are adding is that the out Z3 variables should have the value of that expression, right?
No, I think it's a little bit more complicated than that. If the inputs satisfy certain constraints in terms of range of values that they can take, then the output should give based on the number that it gives, whether it is square or you know,
L shape
and L shape and so on.
Right. So, but like I'm just talking about this like line number 63 here. So what this is saying is just essentially that like whatever expressions we have stored in the res variable.
Yeah, exactly. Yeah, that should be y
are
naught,
equal
y2,
to the
y3.
out Z3
Yeah.
variables, right?
Yeah,
Right.
true,
So
true.
I mean, right. So we could have just passed the out Z3 variable and had like the caller of this function, like just set up the solver for this. Like this is just renaming the expressions in a certain like.
Yeah, I mean,
right?
true. But I just did that because it would be like easier for us to deal with y1, y2, and like the names are good. And it's like you can actually get away with this if you just do this here in the feed forward actual function at the last wait. Yeah. So it's just like and it won't add too much of cost because it's just like a renaming, right, in aliases. So it won't actually add any cost at all to the solver. So it's just convenient. So I did that.
So Z3 will not like just this having an extra constraint that is just a renaming constraint. Z3 is smart enough to detect that it doesn't spend much time on it, basically.
Yeah, sure. I definitely it won't spend any time on it because it's equality. So it will just like when professor will take the classes on DPLNT or all those things, you will understand it's just like a arrow between them that okay, these nodes are equal. So it's just take one pass to it and get the value.
I'm not sure. I didn't understand this particular thing. You know, maybe I don't know how many of the rest of the class did. What exactly are you guys discussing? So what is it that you're adding?
Yeah,
what will be the alternative?
Diganta is basically saying that this line is kind of redundant because I'm outputting the result here, and then I'm saying y0 is equal to the result 1, then result 0, then y1 is equal to result 1, and so on. So I'm just making an aliases, right? This y0, y2, y3, whatever the feed forward output gives me, I'm just creating aliases for them. He's saying that wouldn't it be better if I just do it here, like instead of creating, because they are exactly equal. I'm just saying the res is equal to the out Z3. So he's just saying, wouldn't be like smarter if you just do it here. So I'm just saying that it won't at any cost. It's like
just a programming optimization, nothing logical. Okay.
Yeah, and even it won't optimize the program because there is not at all like negligible cost to this. So I don't think there's any benefit of doing that.
Right.
Yeah, so I think this one, like, okay, so we can, I will post this and you can try more things for this. So for example, you can ask like, can it detect L shape? So for L shape, it would be like that, okay, I think L was 1. So let me just put, okay, just let me show this thing to you. So I'm saying that the y1 is greater than y0, y1 is greater than y2, and y1 is greater than y3. I hope it's correct. Yeah. So I'm just asking it that if the middle part is like reddish, then can it give me a L shape? I hope it's L. Let's check. Oh, cap. Sorry, it's cap. So can it give me a cap for that? And let's see if the model, our network is dumb enough to give us that thing. Okay, it's not. No, it won't give. Okay, so this is giving model is not available. So let me just do the check for now. It will give me unset. So that basically means that our model is not that dumb. So it's smart enough that if your middle part is reddish, then it won't give you, the output won't be, okay, I hope I'm not mistaken here. Yeah, so output
what is expected? If the middle part is red, what it is supposed to give?
So it won't give you cap. So first of all, I checked that whether the middle part is red, then can it give me square?
Is it? It is supposed to give cap.
No, it is not supposed to give cap. It is supposed to give like other or some other thing. It cannot give cap at least. So check is telling us that this property is verified. So if you're in the matrix, you have the middle part red, then it will never give you cap, which is what we wanted because cap was shaped, was like this. So cap is, I think I have cap here. Yeah, cap is like this. So cap, if the middle part is red, it won't give you cap no matter what other things are. So actually network is not that dumb. So that is what you're getting here. So you can actually play with these things and see where a model fails. And this is what verification of this neural network means. So you are just giving some input that, okay, if these constraints are satisfied on input, then whether my output satisfies some constraint. So we'll see something, maybe Madhuka will show ReLU flags later, and that will clarify like what is going on here. So this is, I think, just like doing it manually. We are doing everything manually. So you should, when I post this thing, you just go through this code and see if you are getting it. This is simple thing, the feed forward that you have done, and nothing more than that. And you just play with this.
One moment, I didn't quite understand your comment when you said we are doing everything manually. What do you mean?
So I'm saying we're not using reluplex or anything, which Madhukar will do later, I think, which will be like a black box for this. So you just pass the weights, biases, and the constraint, and it will output whether it's satisfied or not, whether this thing is satisfiable or not. Yeah.
Yeah, but a lot of things are being done automatically here.
Of course, like
you're generating the formulas that in any case has to be done through a program. Okay.
Yeah.
So, but okay, one other thing that I wanted to was, so some of you might be wondering, what is the big deal here? You're creating this whole thing, and is it any different than simulation? You could write a program for simulating the entire neural net and then give specific inputs and then see what the output is. Is this any different from that? Because of all the programming required, you know, one may wonder that. I mean, I'm posing that question, I'm going to be answering that. It is not. It is different from regular simulation where you are giving inputs completely, you know, fully enumerated inputs. That's not what's happening, because what Hitat did, okay, I know Hitat, you explained it, but I'm just re-emphasizing it, okay, that he's only specifying certain constraints on what the inputs should be like, what squares should be dark, you know, red, and so on, and then asking the question for all such inputs that meet that constraint, which could be more than one and several, if it, you know, what is that it gives a certain kind of classification. So which means that you're kind of answering it for by giving constraints, and therefore you will get more definitive answers. And also the other thing is that Hitat also showed that if there is a violation, then it gives a counterexample, an instance of the input for which it is not behaving correctly. Okay, so you know, which is hard in regular debugging. So you know, so I wanted to emphasize that point. I hope.
Yeah. So I mean, there's one thing about C3 solves this SMT solver, of course, that when you do this, like there's 2 to the 16 possibility, right, for the matrices, and if you manually check them, it will take a long time. But there are some pattern that Z3 SMT solver will automatically detect, and it will say that, okay, I don't need to check all these things because they're not giving me anything either way. They will not give me counterexample anyway. So I mean, there are optimization that SMT solvers do so that you get this output very quickly and without actually wasting too much time. So this is that's why we are using this solver for this. Manually checking it will take a lot of time. Might take a lot of time.
Okay, it's 4:50 now.
I'm sorry.
So what should we? Yeah, you know, Madhukar, I guess we don't have enough time to show. What was your plan to show?
Yeah, certainly. So I'll, you know, maybe in another 2 minutes, I'll tell them what I have to show, and then I can show it actually in the next class.
Okay. So then the question is, okay, you could introduce what you plan to show, and you know, before that, Hitat, would you, if you were to, maybe what you should do is to specifically, you know, give some experiments that they can actually be doing. If you could formulate them, then it will be easier. So whereby they could run, kind of run this thing on Z4 for other constraints, and then see what the answers would be like. Okay, and that is one suggestion that I have, and so you can make some exercises that for experiments that they could be doing, so that they will get a
hang of it,
comfortable hang of what exactly is happening.
Yeah, so one more thing before Madhukar starts, like he will just take, I mean, as he said, 2 or 3 minutes, because he'll show that in detail next time. So he's actually working on this, like something like a network for detecting prime numbers. So I have done this here, and if you see this, so it's, I mean, for some reason, it's pretty bad. So I'm just telling you, just take 1 minute. So when you run this, you will see it's not learning anything. It's just giving you like all the numbers are composite. So Madhukar will show you something better, I guess, because his model is actually giving some numbers as prime. And this network is just, okay, I didn't actually tell you. So it's just supposed to take a 16-bit number and output there are two outputs, and it will tell you whether the number is prime or not. So it's like a classification. But of course, I mean, for the record, this is like not that we are trying to get algorithm for detecting prime number. This is just for like an experiment or for demonstration. So I will say that if you have time, when I put this thing on Moodle, you can actually try to tweak this and see, can you increase this accuracy? Is there any way that you can change the input or something? Because I've tried it for Madhukar and I tried a long time, but we weren't able to get like any good results. So if you have any idea on this, then I'd love to we'd love to know that, like how can you make it like detect more prime than there are. Like it's not good. It's just giving composite for all numbers. So you can look at it also that when I publish this. Okay, so I'll just end it here. If there's any question for the last part, then you guys can let me know. And of course, if you have any idea for this prime network, then also let us know. All right, I'll stop sharing.
Wait. I have a technical small question.
Oh yeah, sorry, go on. Okay, I'll share.
No, that's
again.
fine.
Yeah.
So the unknown thing that it outputted for the digit net, is that necessarily a timeout, or could it also be something else?
Oh no, it was not timeout actually. Honestly, it was not timeout. So I waited for like 50 seconds. It was not working. So I just clicked end. So you can actually see it here. So okay, let's wait. So it's just making me wait and wait for a long time. So here it's done. Okay, maybe I made a mistake here, but it was correct earlier. So okay, I have no idea what's the problem. Yeah, it's kind of timeout. Yeah, it was taking a long time, so I canceled it.
Yeah, so does that mean that Z3 will be useless for any non-toy model? Is that, or
no,
could we
no,
maybe
not at all, not at all. So there are some abstraction techniques that Madhukar and Phil actually tell you about, which will be applicable to these large networks. So instead of doing it like naively by all the neurons and just multiplying them like a child, you do some abstraction and you get good outputs, like good results from that. So it's not like
correct. So I mean, answer to your question is, as Madhukar did explain in his, when he introduced this thing, this is still an emerging field. This application area is still an emerging field. Okay, but there are, we will be presenting some papers to where they have applied it. SMT solvers with specialized solvers, I might add, one of which is called ReLU solve or ReLU-Plex or something like that. ReLU-Plex, which when added, they have been able to analyze for the kinds of properties that Madhukar showed, like robustness properties, for networks which are, Madhukar, correct me if I'm wrong. I mean, I think there are 500. I mean, it's pretty big, okay? These are
300 neurons and 10 hidden layers and such things.
Yeah, and several such subcomponents, okay? And the whole thing was even much larger, but they kind of showed some properties for several subcomponents, which each of which was like 500 neurons and so on, okay? So it does scale, beyond what you toyish kind of thing. But there may be some, and also this particular example of primality may not be the best thing for you to do, okay? And I don't know what the source of timeout that Hitarth encountered for that small problem. I would think it should have scaled. I don't know what the source of the timeout was, but that's a data point. So
okay, the source was like my timeout. So it was taking more than 1 minute, so I canceled it. I'm telling you that it's not like Z3 timeout. I don't know whether Z3 will timeout in it or not.
So it could have been in your modeling phase also. Okay. Could be.
So it's working right now, but it's not giving output. So you see, you've been talking for like 40, 50 seconds. I think it's not giving output. So that's why I canceled it. So Sahil, you can try that out. I think I'll post this and maybe you can do something here and make it work.
Right. Yeah. Because we did see in the MCSP class that there were some really basic problems that Z3 couldn't really do. I think it was the pigeonhole was one of them. And
yeah, but that is true. I mean,
pigeonhole is like a canonical example of where it doesn't work.
Yeah.
But that is true. So these are all NP complete problems. So you would expect that there will be very small problems for which it you know, it can stump the thing, but
Right.
that doesn't mean that it is not useful. Okay. Yeah.
Right. Yeah.
Yeah. Because there could be so many typical problems for which you can do. And the other thing is, how do you coax the solver to do it in clever ways? Okay, is also a challenging thing.
Yeah, so I'll stop sharing. I think Madhukar can take from here. And this is not working. Like you can see, this is just waiting. All right, bye.
Yeah, maybe you should, yeah, we should explore that, okay, as to what the real cause of it is and why it's happening.
Yeah, I'll just take a minute. You know, we have already spent a lot of time, and I'll just take a minute. So yeah, so I'll just tell you what I tried to do. And you know, so what I tried to do was I tried to train a network to learn, you know, whether when Hitat showed the example, it had 16 bits. I tried it for 8 bits. So I tried to train a network to learn whether the 8-bit number is prime or not. And you know, I provided some. So for instance, you know, I mean, this is what I did. You can see my screen, right?
Yes. Yes.
Correct. Yeah. So what I did was I gave it exactly one hidden layer, and of course the input layer has 8 neurons, right? Because you have 8-bit numbers. So the number I gave it only 5 neurons in the hidden layer, and I gave it 2 output neurons, one for prime, one for composite, and I trained it over 150. Remember that there are 255 numbers of 8 bits, so I trained it over 150 of them. Okay, and then so this is, we'll ignore this for now. So what I got was these weights and biases of these two layers, right? So one is from the input to the hidden, and the other is from the hidden to the output. Okay, so these are the weights and biases of the input to the hidden, and this is from hidden layer to the output. And then once I did that, what I did was I got these. So these are simply copied pasted from here. You know, these weights and biases are just copied pasted from here. So then I got these weights and biases here, and then I mean the layer says that, you know, the first one, the input layer has 8 neurons, the middle layer, hidden layer has 5, and the last layer has 2. And then what I did was in a very simple way. You know, this may not be the best way of doing it, but you know, it certainly illustrates what I'm doing. So I initialize these two functions, which are, you know, the values, you know, one by doing multiplying all the weights and biases, and the other by, you know, the value by applying the ReLU function on top of it. Of course, I'll go through it in more details in the next class. So I started with, you know, I went on adding these constraints, and then I added the precondition. So you know, for instance, one example that we had given in the last class was that does the network learn that, you know, at least every even number which is not 2 is certainly prime, and then I ran it to and then I ran it to see if I can. So it says it gives me unsat, which says that, you know, it cannot find any even number which was detected as
this is partially correct.
Okay, yeah. So you can at least, yeah. So as I was saying in the class also, that, you know, you may not always be able to specify the entire correctness property, but you can still specify certain desirable properties. So the desirable property here being that, you know, even numbers should not be classified as primes at least. And this is what. So of course, you know, in the next class we will go over it in more details before we begin with another topic.
Yeah, but are you
that's
going
all that
to,
I wanted to show. Yeah.
Now, are you going to put up this thing so they can experiment, or?
Yeah, no, I'm not going to. You know, Hitat has warned me that, you know, the way that I have created this network is something which is an assignment which is due on Monday. So only after the assignment is submitted, I can upload this code.
Ah, okay. Okay, fine.
Yeah, but I'll do that, you know, at least, you know, next class I'll upload this thing, and, you know, people can look at it, and you can write your own properties, and you can.
Yeah, I'll also upload all the Z3 tutorial, especially for those that are still, you know, the few that are not taking yes, that have not, you know, it was a very shortened Z3 tutorial, so I encourage that you type in and try those examples as well, so you will get acquainted with using Z3 on those things. I will upload all the tutorial on Z3. So those are logical variables. Okay, I think it's getting too late. Okay, so I'm getting warning. So yes, that's so we have overspent. So thanks for your, I appreciate your patience, and we should end here. Okay.
Yeah, certainly.